Hey everybody, so this lesson has to do with tonicity and osmoregulation. Okay, so let me get myself out of the way. Okay. Whew, slow. Okay, so real quick review because we talked about osmosis. So what is osmosis? Of course, osmosis is the movement of water molecules from areas of high concentration to low concentration in relation to the number of particles of another substance. So the idea is we're trying to dilute the sugar so that we have the same concentration of sugar to water on each side of the membrane. So when we're talking about tonicity, we're talking about the ability to gain or lose water. And so it depends on the concentration of these solutes that can't pass through the membrane to determine the tonicity. So it can be isotonic, hypertonic, or hypotonic. And we use osmoregulation to control or maintain that water balance, that solute concentration water balance concept. Okay, so animal cells are going to react differently than cells with cell walls. Animal cells in the wrong situations will shrivel up and become non-functional or get so large that they could actually lyse or burst, whereas cells without cell walls may not actually show the physical shriveling or bursting, but they can still swell or have membranes shriveling and become non-functional, but you won't see as dramatic a shift in cells that have cell walls. So animal cell versus plant cell. So cells that are immersed in an isotonic solution, and remember, isotonic is basically saying we have the same concentration inside the cell as outside the cell. So there is no net movement of water. Notice I said no net movement of water. You'll notice as water moves in, water moves out. As water moves in, water moves out. So it's an equal movement on both sides. So it's going to diffuse into and out of the cell at the same rate. Okay, here you'll notice we have a cell that water is moving out of. So cells immersed in a hypertonic solution are going to lose water to the extracellular surroundings. So the concentration of the solutes is higher outside of the cell than it is inside. So water is moving out, trying to dilute those solutes. So it's going to move to the extracellular fluid, trying to dilute that higher concentration of solutes. In this case, typically cells will shrivel and die, but you'll notice that you see the physical shriveling more in the animal cell, whereas the plant cell, you have to look more carefully as you're seeing the membrane is kind of pulling away from the cell wall. So we call this process where we get this space plasmolysis, or some people will say plasmolysis. Where the vacuole is actually shrinking and the plasma membrane is pulling away from the cell wall. And then we have our hypotonic solution. And so hypotonic solution, you'll notice with the animal and plant cell, both have water moving in. So the concentration of the non-penetrating solutes, those other solutes that can't move, the ones that aren't water, is lower outside than in. So the higher concentration is inside, water's going to move inside, trying to dilute it. Cell is going to gain water. In animal cells, they will swell and can actually lyse. With plant cells, they actually work really well in this situation. They actually maintain what we call turgor pressure by taking and utilizing that large central vacuole to help deal with this influx of water. So this brings us to the idea of water potential. Water potential is a property that predicts the direction the water will flow. Sorry, my cats are having a disagreement, it sounds like. Okay, so what we're going to find is this is going to include the effects of the solute concentration, so how many of the particles there are, and the physical pressure of these organisms. Okay, so water is going to flow from areas of what we call high water potential to areas of low water potential. Low solute areas, low solute to areas of high solute. So remember, we're moving from where there's less of the little extra particles to the higher so we can dilute them. But that means that we're going from high water potential to lower water potential. I know it's really weird. And we also, because remember we said the pressure plays in too, so areas of higher pressure to areas of lower pressure, trying to kind of dissipate or diffuse that pressure as well. Okay, so we have a formula. The Greek letter psi represents the water potential. And we measure this in megapascals or bars. 1 megapascal equals 10 bars. So water potential overall is equal to the solute potential, also known as the osmotic potential. And so solute, remember, these are our particles that aren't water. So an increase in solute causes the binding to more free water, therefore reducing the water potential. It's kind of like saying, hey, we're more concentrated. And it is typically expressed as a negative number. Pure water is going to be 0 millipascals because it should have no solutes in it. Then we have the pressure potential, because remember we said it was solute potential plus pressure potential. So the pressure potential is the physical pressure on that solution. So it can be negative or positive relative to the atmospheric pressure. So the reality is, if we're looking at a specific solution, all aspects of that solution most likely are going to be at the same pressure. So if it's in the open air, we typically say that the pressure is 0 millipascals because we're exposing all of it to the same pressure. Okay. So how do we figure out solute potential? Because we've already determined that basically the pressure plays no role in most of our situations. So it focuses on that solute potential. So we have a formula specifically. So that's our solute potential in megapascals or bars. We have the ionization constant. So this is actually something you would look up. And it's all about the number of particles that are formed. If there are no ions formed, the ionization constant is 1. For example, sucrose, which is often used, like we did in the lab, is 1. Then we have the molar concentration. So what was the concentration of that specific solution? And the pressure constant, which in general is 0.0831 liters per liter bars per mole K, or here it is in the megapascals. And we have T, which is the temperature in Kelvin, which, remember, Kelvin is 273 plus whatever the temperature in Celsius is. Okay. So if the concentration of sodium chloride inside a plant cell is 0.15 moles. Which way will water diffuse if the cell is placed in a 0.3 molar sodium chloride solution? Water will leave the cell. It will move from the low solute concentration to the high solute concentration. So if we've got 0.3 molar versus 0.15 molar, right? 0.15 molar inside the cell is less than 0.3 molar. 0.3 is higher. So we're going to move from the 0.15 to the 0.3 to dilute it out. Remember, we're moving from the concentrations, right? Okay, so we didn't even have to do math for that one. The molar concentration of a sugar solution is 0.3 moles. Well, molality. This beaker is sitting on your desk in the open air. Calculate the solute potential at 27 degrees Celsius. And we want to find our answer in bars. Okay, so we have our formula. And we know that negative I is -1 for sucrose. We already talked about that. The C, 0.3 moles per liter. We were given that. R, and why did I choose the liter bar? Because it said find answers in bars. And the temperature, we take our 273 Kelvin plus the 27 degrees Celsius, and we get 300 Kelvin, right? So we've got everything set up. Now we're going to put it in the formula. So we put all the numbers in the formula. And we solve and we get -7.48 bars. Okay. So the hard part is making sure we have all the numbers to set up and answer the question. Okay, so we're using the same information from the previous practice problem. Now we want to solve for the water potential of this beaker of liquid. So water potential is the solute plus the pressure potential. So we have our solute potential, and it said it was in open air, and open air is 0 bars. So we put it in the formula, and we get -7.48 bars. Remember what I said, a lot of times 0 bars is our pressure potential, so it really doesn't have an effect. Okay, calculate the solute potential of a 0.2 molar sodium chloride solution at 30 degrees Celsius. Find your answer in bars. Formula. And let's set up all our numbers. So for sodium chloride, -I is -2. C, they gave it to us in the problem. We use the bar one, and we calculate our temperature in Kelvin. Then we just plug it into the formula, and we get -10.07 bars. Okay, the value for water pressure, psi, in root tissue of a plant has found to be -4.6 bars. If you place this root tissue in a 2 molar sucrose solution at 20 degrees Celsius in an open beaker, so the pressure potential is 0. What is the water potential of the solution? So we know the water potential of the root tissue. We want to know the water potential of the solution and which direction will the net flow of water be. Okay, so start with our solution potential. It is sucrose, so we've got -1. They told us the concentration. We know we want bars, and we figured out our Kelvin from the temperature. Plug it into the formula, and we get a number. But we're looking specifically, we're comparing water potential of one thing to water potential of the other, right? So we've got our water potential is equal to our solute potential, and our pressure potential. So we have our answer here. Now the question is, which direction will we flow? Remember, we're going to flow. Here's our root, here's our solution. Look at the potentials. Water will move into the solution because we're going from lower water potential to higher water, right? Okay, so hopefully that helps you a little bit with some of these things, including water potential, because we have to calculate that a lot. Bye.